So the purpose of this hour now is to give just a brief introduction to climate change and what we know about climate change and what we don't know. So we'll cover some of the topics that we will go more into detail now during the coming week or so. So I'll go through just a list of sort of things we do know about climate and climate change. And one thing we do know is that the global mean temperature has increased during the last century, or a little over a century. So this shows some temperature records from the time during which we have direct measurements of the temperature of the Earth from thermometers and so on. So this is change in temperature. This is in the northern, so this is divided into the northern latitudes, the low latitudes, so around, I guess, more of the tropics, and the southern latitudes. So you see a clear warming trend globally over this time, from like around 1880 to 2000, 2010. Temperature's gone up by about 0.8 degrees Celsius globally. But as you see, it's not evenly distributed, and the path looks quite different in different parts of the world. So temperatures have actually increased more in the northern latitude than in low and southern latitudes. You see also the red lines here are the 5-year average temperature, but the black dots here are the actual year-by-year temperature change. So you see that there's also quite a lot of annual variation in temperature. So this is, of course, an important distinction is about climate and weather. What is the difference between climate and weather? Anybody know? So there's a huge difference between climate and weather. So climate is average weather. So although you can't say exactly what the weather is going to be on the 20th of January in Gothenburg a year from now, you can be quite certain that it's going to be colder than the 20th of June. So climate and weather are two different things. So there is a large interannual variability as well, but you see that there's a clear warming trend. So if you look at the 10 hottest year globally on the record from like the 1880s, then almost all of those are in the last decade, with apart from 1998, which was really warm. So if you look at the decadal average, the 3 latest decades are all warmer than any other decade on the record. So a clear warming trend. One thing that climate skeptics are often pick up on is that the last few years, 5-10 years, the global average temperatures haven't increased very much. It's been fairly stable. Whereas greenhouse gas emissions have continued to gone up. And that seems to be sort of inconsistent. A large part of that explanation from that, or one part, an important part, is you find if you look at the oceans and how the oceans are warming. So these lines here shows the lower line here, the dark blue, it's hard to see, it's the upper 300 meters of the ocean. Then the lighter blue is the upper 700 meters, and this is the total oceans. And you see, so what has happened during the last decade is even though warming of the atmosphere has sort of been stable, fairly stable, and also of the more shallow oceans, but the deep oceans have continued to warm up. So what humans do when they increase the concentration of greenhouse gases in the atmosphere is they create an energy imbalance. So more of the heat from the sun gets trapped in the Earth's system. And that energy warms up the oceans, the Earth, and the atmosphere. And most of that energy, 90% of that energy causing warming, actually goes into the oceans. And this is important, we'll come back to this, to understand why it takes time for the climate to change. The oceans play an important role because it takes time to warm up water. So although you've seen not as a strong climate signal in the atmosphere in the last 5-10 years, if you look in the ocean, you see that we're continually warming up still. Only that more of that warming actually goes to the deep ocean, so we don't see it as clearly if we only look at the temperature in the atmosphere. Was that clear? And we'll come back to this. Daniel will talk more about this, the inertia of the climate system. So here's just a short animation. I hope this will work, showing the sort of geographical distribution of change of temperature. And fortunately, I don't have the legend here. So, but this is relative to, I think, the average temperature. I think it's between like 1960 and 1980, something like that. So blue, it's colder, and you will see more and more yellow and red start to turn up. So that's warmer than the average in that period. So you see up until this time, it's now it's more white. It started very blue, and now things start slowly happening and really getting a big change. And this goes up to 2012. Yeah, so you have, if you look at, it's most clear here in the northern atmosphere, northern latitudes. So you had a strong warming up until like 1940, and then it actually went down almost to the like 1980s, and then started to go up again. And that has to do with the natural variability. One big explanation, we'll come into this, is the role of volcanoes, so volcanic eruptions that sends a lot of dust into the higher atmosphere, the stratosphere, that reflects the incoming solar radiation, that cools the Earth. So you had some volcanic eruptions here that played part in explaining this. This pattern. You see in the southern latitude, you don't see as big a dip here. You see some as well. So that's good. That's one thing you see clearly in this animation. Anything else you spot when it comes to the sort of the pattern of warming here? Yeah, so that is one thing that comes out. Warming you tend to get higher warming over land than over seas. And as I showed, as the last slide also showed, you tend to get more warming in the northern latitude, especially around the Arctic, than in the south. And this has to do partly with what I already talked about, the fact that the oceans take longer time to warm up. Therefore, the warming is faster over land than over oceans. And it has to do with different types of feedbacks in the climate system. As the Earth warms, what happens, and how does that in turn affect climate? And that is an important explanation for the fact that it's warming, more warming here. Also, of course, the fact that you have more land masses in the northern latitudes than you do in the southern, of course. Yeah, I don't have a good explanation for that, but there were there were instances where you had a lot of warming in here. So this is, I mean, I think between the dark blue and the dark red, it's like 4 degrees or something. So I think even though you have fluctuations in Antarctica, then still the temperature is like minus 40 there or something. So I'll come back to that when I show the impact on ice sheets and so on. But I don't know exactly what that is due to. It might also have to do with ozone layer, but I'm not sure. That's speculation. So I can try to look into that actually. That's a good point. I'll try to remember, and remind me if I don't. If you go further back, So this is showing I think this is again only the northern latitudes. Temperature records for the last 2,000 years, using different kinds of proxies. So you can, for example, look at tree rings and see how fast trees have grown, and that is proxy for temperature change. Corals, you have also and other proxies. And you see that so these are different reconstructions. So the further back you go, the larger the uncertainties are, of course. And different studies show different variations, but you have this sort of general, you had a warm period during the medieval period, then you have what we call a little ice age, but these were not global phenomena. So this was for the northern latitudes, but if you look at a global scale, then actually it was much more stable. But in any case, the warming we've seen in the last 50 years or so has been sort of unprecedented throughout this period. And that is clear. That's a good, it's hard to put, so the question, I guess, to rephrase it is, how long does it take to get sort of to an equilibrium over the Earth compared to the ocean?
Exactly.
And I think that I'm not sure how big difference that is.
What is it?
But since we're continually warming, since we're increasing the concentrations and so on, when you have this inertia, there will continue to be sort of a slight difference between the Earth and the ocean. And how fast that will level out, that's a good question. Try to remember that and ask Daniel about that, because I think he will have a better answer than me.
Because I was wondering.
Yeah, so there are time lags for different reasons, and of course, when the Industrial Revolution happened, emissions still were quite small, and other effects, sort of the internal variability of the climate system, and so on, still had a bigger impact. As I said, it was only until like the beginning of the 20th century that fossil fuel emissions were larger than the emissions from deforestation, and there we have other factors that come into play as well. So it's only, and that shows in the temperature record as well, it's only in these last few decades that we really see this clear warming trend. And part of that is this inertia in the system. It takes time to warm up the Earth. And we also see clear effects of this warming. So one very clear effect is the disappearance of the summer ice in the Arctic. So the red line here is where sort of the ice cover was in 1979. This is from satellite photos, and this is the coverage in 2011 or 12, I think. Yeah, 12. Winter ice cover has not changed that much, but in the summer, much more and more of the ice sheet is melting. If we look at loss from the melting of ice sheets and glaciers. So this shows Antarctica and Greenland, and this is the change per year in the last decade or so. You see a big difference between Antarctica and Greenland. So in Greenland you have loss of ice from warming at quite a high rate, whereas in Antarctica there is only here in the west part actually see a large loss of ice, and some parts you actually see an increase in the ice cover, in the ice sheet. And that has to do with the fact, as I said again, that if you have sort of a temperature of minus 40 degrees Celsius, then if it goes to minus 38, it's still cold enough for the ice to persist. And you see increase here because you see changes in precipitation as well. So you see maybe in some places it starts to snow more because of climate change. So it's not a clear trend, but for Greenland you definitely see a huge difference. And this lower graph here shows the loss of ice, and this is in billion tons, from glaciers all over the world, from Greenland, and from Antarctica. I'm sorry about the light figures here. In terms of ice loss that contributes to sea level rise, then most of the largest contribution so far is from glaciers in different parts of the world. But you also see a trend that is actually increasing. The ice is melting faster both in Greenland and Antarctica in the last decade or so than it did before. And this is an area where there is substantial scientific uncertainty about how fast this process is going to go about. And I think Daniel will talk a bit more about that as well. So glaciers, as I said, is one, and here you have, really obvious pictures of what is happening. So this is from one glacier in Austria, a picture in 1875, and the same picture in 2004, and a huge glacier that has more or less just disappeared. So you see this all over the world. This is another glacier in Argentina, in Patagonia. And I always forget to look up why it's called the Uppsala Glacier. I guess there was somebody from Sweden who went there and found it the first time. Picture from 1928 and 2004. And again, huge ice masses that disappear. So there are some places on the planet where you actually see glaciers increasing because you see more precipitation. But almost everywhere you see loss of glaciers. There's this national park in the US called the Glacier National Park, which was founded in an area where there were a large number of glaciers, and I think more than half or even 3/4 of those glaciers has disappeared in the national park. So glaciers are disappearing fast, and this is something that both of course affect biological systems and so on locally, but also contributes to sea level rise. There are a lot of studies starting to look at the impact this has on biological systems. This was like a review article, and I just want to make a few simple points. Looking at studies, trying to look at changes in physical and biological systems and whether they were consistent with this warming from climate change. And first of all, nearly all, in all areas, in all continents, you see that most of the studies are consistent with, you see changes in biological systems, you see spring coming earlier, flowers blooming earlier, birds that are what do you call it, when they make eggs in English? Nesting earlier and so on. Thank you. One clear thing that comes out here if you look at, so this is the number of studies in these cells here. So in the US, this was from 2008, so like 500 studies each. In Europe, you had like 28,000 studies looking at biological systems. In Africa, you had 5 and 9. So there's a large imbalance in terms of the looking at what climate change actually does to physical and biological systems, a bias in terms of the focus of those studies. So there's a lot of things to do in developing countries, as I think you all aware of. This might have changed a bit, but I think this bias still persists. But we see changes. We know that the Earth is warming, and we start to see changes in both physical and biological system from this warming. One thing we also know is that there is a natural greenhouse effect due to the presence of trace gases, greenhouse gases in the atmosphere. We'll spend the next couple of days actually start to looking into what explains this natural greenhouse effect. And this is something scientists have known since the 17th century or something like that. So it's not something new. It's not something that is disputed. And then we know that the concentration of these gases have increased due to anthropogenic emissions. So if you look at the concentrations of the 3 main anthropogenic greenhouse gases, carbon dioxide, methane, and nitrous oxide, over the last 2,000 years, you see this clear increasing trend in the last 100-200 years. So Carbon dioxide concentrations is today up at 390 parts per million in the atmosphere, which is like 40% higher than the pre-industrial level here of around 280. Methane concentrations have increased by about 150% or something, and nitrous oxide concentrations by about 20%. If we go back and look even further back in history, this shows nitrous oxide concentrations, carbon dioxide concentrations, methane concentrations in the atmosphere in the last about 600, 700,000 years. And you see that it goes up and down if you look at carbon dioxide. But anyway, how do you know what the carbon dioxide concentration was in the atmosphere 700,000 years ago? Trees, I'm not sure. That's more for temperature, I think, where you look at how fast they grow and so on. But the main thing here is you drill in Antarctica, for example, we have really deep ice, kilometers of deep ice. You drill down the ice, and inside the ice is trapped small air bubbles with the atmosphere from like 700,000 years ago. So you can actually measure directly then what the carbon dioxide concentration was, what the methane concentration was. So it goes up and down, in part has to do with this cycle of warm periods and ice ages. So you see that in the periods, and here you actually have also a proxy for temperature. So in the warm periods, you have higher carbon dioxide concentrations, and right now we're in a warm period. Some people say this simply, oh look, when the carbon dioxide goes up, then temperature goes up. But it's not that simple. So this doesn't imply causality. It doesn't mean because carbon dioxide concentration goes up, temperature goes up. Actually, if you look carefully at this, temperature starts to go up first, and then carbon dioxide concentration follow. And yeah. And why is that? That's counterintuitive, right? So, well, the first thing is what causes these changes in temperature in the first place? That has to do with the Earth's orbit around the sun and the tilt of the Earth and so on. That sort of changes the energy balance slightly of the Earth. That has effect on the carbon dioxide concentration. So, for example, as it gets warmer, as the oceans warm up a bit, they can hold less carbon dioxide. So carbon dioxide is then less soluble in the oceans. So the oceans will start to emit some carbon dioxide. Then carbon dioxide is a greenhouse gas. So that will increase the temperature even a bit more, which means even more carbon dioxide will be released into the atmosphere and so on. So this is one example of these important feedback slopes that has to do with that affects climate to a large extent. And we'll talk a lot about those because those are important. Yes, question? That's a good question. So how can you be sure that the air that trapped there, that the concentrations actually reflect what it was then, and it hasn't reacted with other chemical compounds and so on? And I can look it up again. It's a good question. I don't have a good answer, but I guess I think carbon dioxide will sort of become in an equilibrium quite quickly. So, but I think they also, I guess, they can also correct for those kind of changes. But I don't think carbon dioxide will interact so much with the other chemical compounds. But it's a good question. I'll look it up. Yeah. So if we look, and now they've gone back to like 800,000 years, and compared to the historical records, then clearly methane concentrations, carbon dioxide concentrations is higher than they have ever been in the last 800,000 years. Yes, or I mean that is another part. We can be. I mean, it's virtually certain that the reason that they are so high is because we are emitting these gases. So, oh, sorry, wrong way. So we look at the anthropogenic carbon or emissions of these gases. So this is carbon dioxide emissions from 1970 to 2004. Well, this is fossil fuels, the red here, and this is from other, which is mainly cement manufacture. So these emissions have increased dramatically over, and if you go back even further, and they are continuing to increase. So today I think we're emitting about 10 billion tons of carbon, which is like 37 or 36 billion tons of carbon dioxide every year. So this has been a steady increase. So the reason that these concentrations have gone up is due to anthropogenic emissions. So for carbon dioxide, mainly fossil fuel use, but also here are the emissions from deforestation and from decay of peat and so on. Primarily from deforestation in tropical Asia, where you have peaty soils. And emissions from methane, which is the second most important anthropogenic greenhouse gas. And here it's both emissions from the energy sector. So natural gas is methane. So when you produce natural gas, if you have leakage, you get methane emissions. Coal mines and so also you often have in the coal seams, you also have methane that leaks out, so you get methane emissions. Then you have a large share of the methane emissions are from the agriculture sector and mainly from ruminant animals, cows and sheep and so on. There's also some emissions from the waste and so on. And then nitrous oxide, almost all of the emissions is from agricultural soil. So when you fertilize agricultural lands, nitrogen fertilizers, you get emissions of nitrous oxide, which is a very strong greenhouse gas. So this is from one of these IPCC assessments. So this is in 2004. Then you can convert this, and I will go into this. And so how can you compare emissions of different greenhouse gases on one scale, so to say? And then you can calculate what you call emissions in carbon dioxide equivalents. But this is not unproblematic because different greenhouse gases have different strengths, but they also have different lifetimes in the atmosphere. And you sort of have to weigh this together to get an equivalent measure. But if we measure this in this carbon dioxide equivalent, then like 3/4 of the emissions are carbon dioxide, 14% methane, 8% nitrous oxide, and then a minor share of what you call F gases, which is these freons and so on, and their replacements, HFC and so on, which are some of them very, very strong, potent greenhouse gases, although the emissions of them are quite small in physical terms. They are very strong. Okay. Any questions so far, by the way? Or there have been good questions, but please continue to stop me if there are things you want to. Yeah. Alejandro?
It was like a curiosity from your question, because they make a measure from this size samples from one specific place in the world, which is Antarctica.
Yeah.
How is that represented?
So unfortunately I don't have the picture here, but so measuring carbon dioxide concentration directly in the atmosphere from year to year started in I think the 1960s by a man called Keeling. And at a place at Hawaii, Mauna Loa. And some of you might have seen this curve. So they started measuring, and then measure one point, then measure a few times a year, and it started to go up, and then went down again quite drastically, and then it went up, and you got this wave pattern of carbon dioxide concentration in the atmosphere. And why was that? Well, yeah, no, it wasn't something specific for there actually. You can see this in the northern hemisphere, that the concentrations go up and down over the year. And that has to do with, so carbon is all the time exchanged between the atmosphere and with living plants. So when plants grow, they take up, through photosynthesis, they take out carbon dioxide from the atmosphere, store that in woody biomass and leaves and so on. But what happens in the northern hemisphere, we have these, clear seasons is then in spring, plants grow, they capture carbon dioxide, and sequester it. Then actually the concentration goes down. And then in fall, they shed the leaves and so on. That biomass decays, releases the carbon dioxide again. So there you see this trend. I think I'm not quite exactly sure. I haven't seen but I think it's much less pronounced in the southern hemisphere. You don't see this clear. So if you look at it, it's a good point. So if you look at, for example, it's more clear with methane emissions. Some methane concentrations differ substantially between but I can look up the exact, but it's a clear difference in the methane emissions between the northern and the southern hemisphere. And the reason is in both of the hemisphere you have quite good mixing of the atmosphere that goes quite fast. So you get more or less the same concentration in the whole hemisphere. But the mixing of air between the two hemispheres is much more slow. And because of the methane is so much emitted from especially natural sources, from land, from decay of organic matter and so on, and you have much more land on the northern hemisphere, there is actually a smaller methane concentration in the southern hemisphere. So you see a difference there. But it will, again, you get this lag and how fast it catches up. Of course, much of the carbon dioxide emissions are also in the northern hemisphere. So you see a lag there also, but not as big. And that also has to do with the lifetime of carbon dioxide in the atmosphere is much longer than methane. So because of the short atmospheric lifetime of methane, then much of the methane will be broken down before it actually gets sort of transferred to the other hemisphere. So there is a difference in concentrations over Earth, and depending on but generally you talk about these as well-mixed greenhouse gases. So their concentrations is roughly the same all over the Earth, although there is a slight difference between northern and southern hemisphere. Yeah. So if you measure, it's a good point. So if you just measure this from the ice cores in the Antarctic, is that really representative for the whole globe? So the short answer is yes, although it might be a small difference. But these are, as I said, well mixed. So in that sense, the concentration is fairly the same all over the planet. You can, if you compare with some of the more short-lived pollutants like sulfur dioxide or other nitrous oxides, which have a lifetime in the atmosphere of maybe days and weeks, those are not well mixed. Those will change, they will differ from one town to another, or from one country to another, and so on. But these are fairly the same over the whole globe. Good question. Okay, so we know there's a natural greenhouse effect that is due to the presence of these greenhouse gases in the atmosphere. We know that the concentration has gone up due to anthropogenic emissions. So what we also can say with more or less complete certainty is that the first order effect of this is global warming. What we don't know is exactly how sensitive is the climate to these increases in greenhouse gas concentrations. And we'll talk about a bit. And an important aspect of this is understanding these feedback loops. So even though we can say with quite high certainty what sort of the direct physical effect of doubling the concentration of carbon dioxide in the atmosphere is, a warming of the Earth of maybe around 1 degree Celsius. The knock-on effect that has, that will affect both the concentration of other greenhouse gases and so on, and other parts of the climate system, what the net effect of that is, we can't really say with certainty. So today we say that, well, a doubling of greenhouse gas concentrations in the atmosphere will lead to warming of maybe between 1.5 or 4.5 degrees Celsius, which is quite a large span. So there's still quite high uncertainty around how sensitive the climate is to perturbations. And that is something Daniel will talk more about as well. Then we know that the impacts of climate change can be very serious, although again, uncertainties are very large. So, I mean, the first order effect is we have temperature rise. That affects sea level rise, both through oceans expanding as they get warmer, but also mainly then through the melting of ice caps, glaciers, and Greenland and so on. If the whole of the Greenland ice sheet would melt, we would get a sea level rise of around 6-7 meters. And it's uncertain how likely that has to happen. I mean, it's a process that will take a very long time. But maybe for a warming of 2 degrees, this is a process that will start to happen. But there are large uncertainties here. We get precipitation change. Generally, what you can say is that places that are already dry will become even drier, and places that are already wet will become even wetter. But there are large regional differences here, and this is an area where you have large uncertainties and actually understanding, trying to sort of scale down these global climate models to what is actually happening in a certain region or locale. And that then will have knock-on effects on access to fresh water, health impacts, spread of malaria, impacts on productivity in agriculture and forestry, which can be both positive and negative. Again, with sort of climates in a sense becoming more extreme, or at least the sort of wet areas becoming wetter and dry areas becoming drier. Northern latitudes, which are colder, will tend to, in many cases, benefit from warmer temperatures, longer growing seasons, and so on. Whereas tropical areas and so on that get even hotter and drier will often lose out here. Of course, have impacts on ecosystems all over the world, and then you have sort of more extreme things where things become even more uncertain. Are we seeing more storms because of climate change or not? Or are we seeing more sort of stronger hurricanes or not? And there are still large uncertainties. And we'll talk a bit about, in the course when we go into the economics and sort of discussing cost-benefit analysis of climate change mitigation. What do we know about these, and what is the possibility of actually putting a monetary value on this? Good question. So first, it's important to distinguish between the ozone layer and the greenhouse effect. They are interrelated, and we'll talk about that. So the loss of ozone in the higher, the stratosphere, the higher part of the atmosphere, actually contributes mainly. I'll have to. This is not straightforward and complex, but it has a minor effect on the climate. So that is one thing. So it's important to keep those two separate those, and we'll talk about how they interact when we come into this. The other thing is, so about the ozone layer, whether it's reversible or not. And the thing is, ozone is constantly created in the stratosphere from this high level radiation, this UV radiation from the sun. But then it's broken down also by these, what we emit, this F gases, freons and so on. But if we stop emitting those gases and eventually they disappear from the atmosphere or broken down, then the ozone layer will rebuild again. And I think this is, again, I'm not completely sure, but we've been really good at reducing the emissions of these gases. So the ozone layer is actually sort of regenerating, I think, on a global scale. So it's not an irreversible process, but it's a good question. Okay. So we know there can be large impacts from climate change, although it's uncertain how large they will be, and it depends on how sensitive the climate is to our emissions. So if we want to avoid the worst impacts of climate change, we need to reduce emissions of greenhouse gases quite substantially. So this is, so this is our historic global energy use So today, hasn't been updated in a while, but today maybe around 80% of global energy use is from fossil fuels, coal, oil, natural gas that emits carbon dioxide as we burn it. If we want to try to limit the warming, so far globally we warmed the Earth of about 0.8 degrees. What a lot of people are talking about today is saying so maybe we can't avoid further warming completely. Partly because of this inertia of the system. We already sort of committed ourselves to further warming because even if we would stop emitting greenhouse gases completely today, temperatures would continue to go up because of this inertia in the system. So we can't avoid warming completely, and we can't avoid maybe further warming either, but maybe we can stop warming at 2 degrees Celsius. Maybe that's a reasonable target, something that would avoid the worst impacts of climate change. Well, then if we want to reach that and the climate is quite sensitive, maybe we have to, by 2050 or 2070 or something, have no net emissions of carbon dioxide to the atmosphere. Which means that we have to phase out over that time period the use of oil, coal, and gas, at least unless we capture the carbon dioxide released when you burn them and store it someplace else. At the same time, global energy demand is increasing because we are getting more people, we are getting richer, and so on. So the question is, what do we fill this gap with? So these are so one thing now. I talked about the 2 degrees target, which is sort of discussed in climate negotiations globally and so on, and as a basis for sort of commitments to reduce greenhouse gases. But one question we'll talk a lot about now in the courses, and this is something we've added this year, is looking at this mainly from an economics perspective. So how do we go about setting a target for emissions of greenhouse gases? How do we weigh the costs of reducing emissions of greenhouse gases against the benefits of doing so? Can you do it formally in this, for example, like an integrated assessment model like DICE? What does that actually tell us? And what are the uncertainties? What are the important factors in these models that decide whether the outcome is that, well, we can actually continue to increase carbon dioxide emissions to 2050, and only then we need to decrease them? Or some other models that can say, well, we need to start reducing emissions drastically today. So we'll look into that. And then we'll look into what technologies can contribute to filling this gap, depending on how big it is. So how much can we reduce demand for global energy by increasing energy efficiency and maybe see some changes in lifestyle? And what role can be played by different renewable energy sources, carbon capture and storage, nuclear power, and so on, to actually solve this global puzzle? Yeah, so are everybody familiar with the term geoengineering? So geoengineering is sort of more drastic solutions to try to reduce warming by, for example, one example could be injecting sulfur into the stratosphere to increase the amount of solar radiation that's just reflected back into Earth as a way. If we can't do this, then maybe we have to resort to faster and simpler, and that's a huge debate because there might be other effects of that we're not sure of, and so on. So, but it's interesting, and of course, the longer we go on and continuing to emit greenhouse gases without abating them and seeing effects of that, the more pertinent that discussion will be. So, we haven't really included it in the course so far, but maybe we should think about it. I mean, please bring it up if you in the discussion. The potential is yeah. So that's one of the one of the issues we'll discuss during this week. But it's substantial enough that it actually can make it can have a huge effect. Okay. Lina, yeah, you probably know this better than me because you're actually energy system model. Yeah.
Yeah. Is that a common projection of global energy demand that you show there? You don't have to give me the source or anything like that.
No, this is more of like a back of the envelope calculation. I think this is based on sort of, in 2100 we're 10 billion people, we have the same average and energy intensity as like OECD countries today. And then we end up with sort of going from 400, actually now we're more like at 500 exajoules of energy to like 2,000 exajoules, so like a 4-doubling of global energy demand. So it's, that would be sort of a business as usual, I would say. It's not, I mean, it's a huge range of extrapolations, depending on what you assume in terms of technological advance and GDP growth and so on. Yeah, so this is sort of tilting this. So if we assume that population is the same and GDP is supposed to be the same, how much can we sort of push this down?
Yeah,
how much can we increase efficiency, and how much can we sort of change maybe the composition of the economy? So
one of the things that would make this white part actually fall, not to make it zero, would be a complete reduction.
Yeah, exactly.